On to number 4, where we actually don't have to do any kind of math, we just have to figure out what type of distribution it is. So I'm just going to go through the checklist very quickly. The probability the student passes a written test for their pilot's license is 0.75. What's the probability the student will fail the test on the first attempt and pass it on the second? So we have two outcomes. They either pass or they don't. Pass or fail. I'm going to work under the um, assumption that each time they take the test, it's independent. Each test is independent. The probability that they pass, it says, is 0.75. And what's the probability the student will fail in the first attempt? So in other words, we're looking for until success. So right here, when we get to number 4, this tells us we're in a geometric distribution. Number 5, of students 16 to 18 with A or B averages, 78% cheated to get higher grades. 10 randomly selected students who attended college or plan to attend. Did you cheat? So we're looking for the probability exactly to answered no. So again, let's just go through our checklist to see what happens. There are two options. They either cheated or didn't. Each student is independent. We have the probability that they cheated. We're told is 0.78. And this time we have a fixed number of trials at n equals 10. Right here, by the time we get to number 4, we realize this is a binomial situation. All right. So, on to number 6. Keno is a favorite game of casinos. Basically, there's balls numbered 1 to 8. 20 of them are chosen at random. And players that have already selected a bunch of numbers, right, you mark a number, and if your number is one of the 20 that is pulled, you make $3. So 20 of the 80 are chosen. So basically, you have a 20 out of 80 chance to win. So our probability of winning here is 0.25. What's the probability distribution on a single play? So the easiest thing for us to do is probably just to go ahead and set up a table. So X will be the number of times played, or times 1, I guess we should say. So on a single play. So really, there's two outcomes. We could either win 0 times or win once. The probability, again, that we won was 0.25, which means the probability we lose is 0.75. So there's part A right there. Just filling in that table. For part B, what is the mean payoff? So all I'm going to do there is let's just create a table where we'll say, y equals the payoff. So for us, if we don't win, the payoff is $0. Oops, sorry, I got X sitting there, that's Y. And if we do win, the payoff is $3. Well, the probability that we win, we've already seen is 0.75, 0.25, so we're just looking for expected payout. So that's 0 times 0.75 plus 3 times 0.25. So our expected payout is about 75 cents a play. And for part C, what is the casino's, in the long run, how much does the casino keep from each bet? Well, we had to pay $1 to play. Sometimes we win 3, sometimes we win none. The expected, right, if it's $1, we take out our expected winnings, which was 75 cents. That means the casino is keeping 25 cents per play. So for number 7, we're going to use this table. And this is just going to be basically an exercise in knowing when it's appropriate to combine certain things and whatnot. So x plus 50. If we just add 50 to every value in x, so the expected value of x plus 50, that will cause the mean to shift up to 100. But remember, when you add, that won't affect the standard deviation. It'll still be 8. For B, 10 times y. So when we multiply, you multiply the mean, and this time, with standard deviation, we're not combining any random variables, we're just multiplying everything in a set by 10, so the standard deviation gets multiplied by 10. X plus 0.5y. My suggestion here, let's just redo the table really quickly as we combine these variables, except this time we're going to do 0.5y. So there's our mean and our standard deviation. X is not changing, but y is going to get cut in half. So now the expected value of x plus 0.5y is 50 plus 50, 100. Standard deviation of x plus 0.5y. Remember, now we're combining two different variables. We never add standard deviations. We always add variances. So in other words, 64 plus 39, or 64 plus 9, excuse me, as I look at my answer, that expected, the new standard deviation is going to be 8.54. So again, you can see that variation went up. For D, x minus y. So we're going right back to the original table. So the expected value of x minus y, 50 minus 100, negative 50. And even though we're subtracting these variables, we're still combining them, which means we need to add variances, and that's going to be 10. And then last problem, where they're asking us to do x1 plus x2. In other words, this is kind of like the Plinko where we did a chip after a chip. So the expected value of x1 plus x2, well, that just means add x twice. So that's 50 plus 50, which is 100. Standard deviation of x1 plus x2 would be 8 squared plus 8 squared. Again, add variances. So 60 square root of 128, which is 11.31. And finally, number 8, premature births. They're born more than 3 weeks early. 10% of all live births seem to be premature. So let's suppose that there are, so the probability that we get a premature birth is 0.10. We're going to take 250. This is a pretty big sample size. And we're going to say x equals number of preemies out of 250. So here we go. Just jotting down that information. Can we allow for normal approximation? Well, first off, is it binomial? There are 2 outcomes. They're premature or they're not. Each birth is independent. The probability that we get a premature birth is 0.10. And we have a fixed number of trials, n equals 250. So it is binomial. And then the other 2 things we need to check. 250 times 0.1 is 25, greater than or equal to 10. And p is greater than 10. And q, 250 times 0.9 is 225, also greater than or equal to 10. So all 3 stipulations are met for a normal approximation. That's how we justified our answer. For part B, what's the probability between 15 and 30? It's the probability that x is between 15 and 30. Since we know it's a normal distribution, let's just go ahead and move through this thing. We need 2 z-scores, z1, z2, so we got a critical value of 15, and we got a critical value of 30. So we need to get a mean. We need a standard deviation for this. So remember, this is a binomial situation, so the mean is just n times p, 250 times 0.1, which is 25. So there's that. And we need a standard deviation, which is the square root of n times p times q. And for us in this situation, that's 4.74. So we've got our setup for our z-scores. If we've at least shown that, we're at least showing that we know how to set this thing up. Quick look at a normal curve if you want. This thing is going to be centered at 25. So this is 29 point. This is 20.2. 0.26, 29.74. So we're going from 15 to 20. 15 is actually just below 2 standard deviations. So here's 15. 20 is just, or 30, excuse me, is just above that. So there's 30. So we're looking for that probability. So the probability that we are between 15 and 30. We can go to our normal CDF now. Lower bound 15, upper bound 30. That probability should be 0.84. Of that, uh, most of that data is between 15 and 30. And then for part D, what's the probability that fewer than 20 births, so the probability that we have fewer than 20 live births, or 20 premature births out of the 250 live births. So again, here, critical value is 20. We just saw the mean is 25. The standard deviation is 4.74. That's a z-score of negative 1.05. So we could draw a quick curve for that. Centered at 25. 20 is going to be just below 1 standard deviation. So we should be somewhere close to 16% using my empirical rule. And when I plug that in, 0.146, not far off, about 14.6. So just to answer the question fully, the probability of fewer than 20 births is 0.146, excuse me. So there's my answer in context, just like we've done in the past.